Okay, this is part 2 of graphs of other trig functions. So if you didn't watch part 1, please make sure you go back and watch part 1 first. And if at any time you want to pause and rewatch, go ahead and feel free to do that. So number 1 says sketch the graph of y equals 2 cotangent of x over 3 by hand. So we're just going to go through that checklist again of all the important parts of a graph to look for. So there is no amplitude for cotangent and tangent, but we do have period and phase shifts. Now, we're really only going to be talking about, when we graph, we're going to be looking at period changes. We're not going to really do a whole lot with graphing of phase shifts with the trig functions that are cotangent, secant, and cosecant. So let's just look at the period change here. The period is 180 over 1/3. 1/3 is the number in front of x. So that actually turns out to be, if I multiply, that's actually 180 times 3, which is 540. Or in radians, that would be 3 pi. So when I sketch my graph, I want to make sure that I have a period of 3 pi. So first thing I'm going to do is just look at the original cotangent graph. So I'm gonna put in my y equals 1 divided by tangent of x. Make sure you're in radians if the graphs aren't looking right. And also do zoom 7. That'll make it look nicer trig graph. And it'll have it automatically do increments of 90 for you. Okay, so this is what cotangent normally looks like. Cotangent, if I look at just this one period here, this period of cotangent goes from 0 to 180. So I want to go all the way to 540, so I'm going to really stretch this out. And I'm going to use 3 pi instead. It's going to be a little bit easier to label. So I've got pi, 2 pi, 3 pi. So I'm going to draw in my asymptotes. When you draw a graph, you only have to draw one period. And then it's going to make the same shape, but the middle would be between pi and 2 pi. And it's going to look like that. So if I want to check my work, I'm going to go to y equals, and I'm going to type in 2 cotangent. So that would be 2 divided by tangent of x over 3. And you can see these are going to be a lot bigger, but we're looking really at the next one. That's the one that we're interested in. Yep, and it goes from 0 to, these are increments of 90, so 3 pi. Okay. So let's take a look at number 2. Use a graphing utility to compare the graphs. So it looks like everything's the same except for one is sine and one is cosecant. So let's use our calculator. Go to your y equals. It's the glare from my lights there. I'm trying to get rid of it for you. So I'm going to clear that out. I'm going to type in 2 sine of x plus pi over 4. And I'm going to write down how we're going to type in the next one. The next one would be 2 over sine of x plus pi over 4. Okay, hit graph. So the first one in my blue function is my sine curve, but it already has some stuff going on with it. The amplitude got changed, and it has a phase shift. Now the other graph has the same amplitude change and the same phase shift, but it's a cosecant graph. So they actually have similarities. But remember when we did part 1, sine is the opposite of the cosecant graph. It's the reciprocal. So anywhere where sine crosses 0, cosecant's going to have an asymptote. Anytime where sine has a maximum, cosecant's going to have a minimum. So they actually have a lot of things in common. They have, and I'm going to write this down, they have the same amplitude of 2. They have the same period of 360. And they have a phase shift, both of those. And the formula for phase shift is negative c over k. So negative c is this number right here, pi over 4. K is the number in front of x. So negative pi over 4 is our phase shift, which means this got moved to the left. Okay, let's do the same thing with number 3. Use a graphing utility to compare the graphs of y equals cosine of 2x and y equals secant of 2x. So before I graph it, their amplitudes are both 1. Their periods, if I use the formula, 360 over k, which is 2, is 180. And there's no phase shift. Okay, so let's graph this. I'm going to clear out my graphs from before. So I have the cosine of 2x and I have secant of 2x. That's 1 divided by cosine of 2x. So my first graph is cosine. Now these are scrunched in because their period is not 360 anymore, it's 180. So it's a smaller graph. And secant should be the reciprocal of cosine. So they should match up perfectly. Anytime cosine crosses the x-axis, secant's going to have an asymptote there. Okay, so let's go to the back. We're going to look at damping functions. So these are pretty cool because the damping function is a combination of two functions put together. Typically, it could be like an algebra function with a trig function. It could be a logarithmic function with an algebra function. So you're kind of smushing two functions together. So for example, if we look at number 1, we have x times sine of x. So we have an algebra function, and I know x looks like this. It's a diagonal line. And I have a trig function, which looks like this. So when we graph this, let's go to our calculator and let's type this in, x sine of x. Now if you have the Inspire, it's probably not going to graph this unless you put x times sine of x. So if it doesn't graph nicely, just go back and put in a times in between. So let's go to the graph. And it's going to look kind of strange. I'm also going to zoom out a little bit. So you can see a little bit more of the graph. I'm going to sketch this on my paper. Okay, so what I want you to do is go to your y equals and let's just type in plain old x and hit graph. There's that algebra function. So if you notice, what happened is the trig function kind of meshed in with the x. So it took that sine wave and it kind of combined it with the x. So now it goes perfectly along with x. So that's what's going to happen. Sometimes you can kind of like tell what they're going to look like, but if you don't, it's okay. You can graph it, but you should be able to tell once you graphed it why the shape looks that way. Okay, so let's look at number 4. So let's type this one in. Here we have a logarithmic function, an exponential function. We have e to the negative x. And then times, so if you have the Inspire, put your times in, sine of 3x. So hopefully you remember e to the x, but it's negative. It's a decreasing exponential function. We're going to combine that with the sine graph. So let's take a look at the graph. I'm still zoomed out, but that should be okay. This kind of looks crazy right now. So if you want to go back to your zoom trig, it might look a little nicer, maybe not. Yeah, it kind of looks nicer there. Okay, so I'm going to draw a graph of this. So it goes, kind of looks like it goes up and down and then eventually tapers out. Now, if I were to graph just the logarithmic function, the exponential function, e to the negative x, you should see that graph and the sine graph kind of mesh right into it. So it kind of uses it as a boundary. So that's called a damping factor. When you have two different functions combined together, they kind of take the shape of each other and mesh them together, so it makes one graph with the components of both. Okay, so that concludes our part 2 lesson. Make sure you look over your notes that you're ready for your first quiz. And feel free to go back, rewatch anything that you struggled with, or email me with any questions.